Once look at this the mechanism. Girls are getting, other girls please respond. Are getting or others? Right. See, first category, first type of mechanism. This carbon hydrogen bonded electrons are shifted towards carbon, and chlorine is taking bond pair of electrons, Okay. This is called heterolytic fission. This type of cleavage is called heterolytic fission because chlorine is taking a complete bond pair of electrons. 2 electrons are taken by the chlorine. Okay, so it is called as heterolytic fission. See, which type of carbene is formed? Okay, we know the name of the product is carbene, intermediate is carbon, but which type it is? Let us see. Actually, around carbon 4 orbitals are present. Okay. In this orbital, just imagine. In this bond, 2 electrons are present. Okay. When hydrogen leaves, the 2 bonded electrons are entered into one orbital. Okay. Here another orbital is there, but chlorine is taking its electron and electron of carbon also. So this orbital will become vacant. See, very simple thing. Once again, listen all of you. This carbon and hydrogen are in the bond. Imagine between these two, one orbital is present, hybridized orbital. Imagine it as a hybridized orbital. Okay. Hydrogen is losing its electron and it is leaving. That extra electron is entering into the same orbital only. Clear? But in this case, imagine one orbital, hybridized orbital is present here. Okay. Chlorine is taking 2 electrons and leaving vacant space. Okay. So vacant orbital is formed. When heterolytic fission takes place, one vacant orbital is formed and paired electrons also formed. Paired electrons. See, spin multiplicity. One concept is there, small topic. Spin multiplicity. This is additional information. Very easy topic. Just listen once and leave it. Spin multiplicity formula is 2s plus 1. 2s plus 1. Let us go to homolytic cleavage. Heterolytic cleavage gives singlet carbon. Homolytic cleavage. I mentioned clearly, you can understand by reading the PDF. Homolytic cleavage. See, here 2 bonded electrons are present, right? This bond will cleave homolytically. Okay. One orbital. See, hydrogen is taking 1 electron, leaving single electron in the orbital. Here also chlorine is taking 1 electron only, leaving 1 single electron in this. Got it? See the difference between heterolytic cleavage. In heterolytic cleavage, chlorine is taking two bond electrons. That's the vacancy is creating here. Hydrogen is leaving its electron given to carbon and it is leaving alone without electron. That's why paired electrons are present at this carbon. Clear the difference? In the homolytic cleavage, in this orbital one electron will come. Here also one electron will come. One electron and one electron. So spin multiplicity. Spin multiplicity. Tell me spin multiplicity. What is the formula? 2s plus 1. Tell me. Spin clockwise. Both are clockwise on the right. 1 by 2 plus 1 by 2. 1 by 2 plus 1 by 2 is 1 by 2 plus 1 by 2. 1. 2 into 1. 2 plus 1. Okay. This is triplet carbon. Okay, number of single electrons are present, but we have to take their spin actually. The S stands for not number of single electrons, the spin value, spin value. Here 1 by 2 plus here 1 by 2, edited. So 1 by 2 plus 1 by 2, 1. 2 into 1, 1. Total 3. So this is triplet carbon. Triplet carbon. Triplet carbon is diamagnetic. Before that, what I wrote is paramagnetic or diamagnetic. Diamagnetic. Okay, this is paramagnetic. Why this is paramagnetic? Single electrons are present. Mention that point also. Okay, but here one small correction. Instead of taking 1, take 1 by 2. Spin values we have to take. We know according to spin quantum number, clockwise plus of, anti-clockwise minus of, that we have to consider. Have to take. In the last case also, just a second. In the last case also, one is 1 by 2, right? Anti-clockwise. Another one is clockwise. Look at this. Plus 1 by 2, minus 1 by 2. You know, in single orbital, two electrons do not lie in the same direction. One is clockwise, one is anti-clockwise. One is plus half, one is minus half. Both will be cancelled. That's why I took 0 here. Okay? Not single electron. Okay, by doing calculation on the paramagnetic property, I habituated for that and explain like that. Actually, paramagnetic property is color. Color property, paramagnetic property, condition is single electron only. That's here we take the values. Okay? 1 by 2, minus 1 by 2, 0. Here both are in the clockwise. 1 by 2 plus 1 by 2. So 1. So 2 into 1. Here plus 1 is there. So 3. Triplet carbon and a singlet carbon. We have two types of carbon, singlet and a triplet, which is paramagnetic and which is diamagnetic. See this. Okay, triplet carbon is the paramagnetic because single electrons are present. This is 1 electron, this is 1 electron. But while calculating this, we take the plus half, minus half. Clear? Right. So this is additional information only. If you are interested, then go through it. Otherwise, read up to this last property. Okay. Up to this. Right. Is there anything else in that first chapter? I think we covered aromatic nucleophilic substitution also. Completed aromatic nucleophilic substitution. Girls, respond. Are you there? Hello. Aromatic nucleophilic substitution reaction. SN1 is completed, SN2 is completed. SNAR. What is its abbreviation? Abbreviated as SNAR. SNAR. Aromatic nucleophilic substitution. Aromatic nucleophilic substitution is substitution reaction takes place on the benzene ring. Benzene is aromatic. Before that, we have seen substitution reactions in normal compounds, non-aromatic. Okay, haloalkanes. But here we see the substitution reaction on the benzene. Benzene is aromatic, that's the name is aromatic nucleophilic substitution reaction. Look at this. Cl OH minus is the nucleophile. One nucleophile is coming and other nucleophile is leaving. This is simple example of aromatic nucleophilic substitution reaction. Substitution only, but it takes place on the benzene, on the aromatic. That's why ARSN. Okay, this is simple example for aromatic nucleophilic substitution. One important condition is required. See, if I do not give N-O2, if I give only chlorobenzene, then chlorobenzene do not participate in the aromatic nucleophilic substitution. Very important. Aryl halides undergo nucleophilic substitution when strong minus M groups are present in para position or alpha position. Very important condition. Okay, this is chlorobenzene aryl halide. When this compound undergo nucleophilic substitution, when strong minus M group is present in the para position or alpha position, we will know the reason also. Okay, next in the mechanism you know what is the reason why we need a strong minus M group in ortho and para positions. Ortho or para, not and. If both positions are present, then also it undergo fastly. Clear? But at least one NO2 should be NO2 or any cyanide, aldehyde, carboxylic acid, any minus M group should be present in para position or ortho position. If I give plain chlorobenzene by removing this, if I remove this, then it do not participate in the nucleophilic substitution reaction. Okay, so first I will write that condition only. Aryl halides are haloanes. Haloanes with the strong minus M groups in ortho or para positions only undergo SN type reactions, nucleophilic substitution type reactions. Okay, haloanes with a strong minus M groups in ortho para positions only undergo SN type reactions. Okay. Let us start one example with the mechanism. Mechanism is important. Okay. Have you completed that statement? See this. Example with the mechanism. Chlorine and NO2. NH2 negative is the nucleophile. NH2 NO2. Cl negative, NH2 negative. Nucleophilic substitution. Okay. Right. Let us see the mechanism. And we know the role of NO2 also. I given one statement, presence of minus M in para position or the position. Why? With the help of mechanism, we can know about that statement. Right? Okay. NH2 negative is a nucleophile. NH2 negative is a nucleophile. Nucleophile needs positive charge. Nucleophile tries to attack positively charged carbon. Clear? Because it is negative, so it needs positive center, electron deficient center. Clear? But see, on this benzene ring, is there any positive charge? No. But when positive charge will be created, when you shift any one of the bond towards particular carbon. Clear? If we shift any one of the bond towards particular carbon or towards particular atom, see here one pi bond is there. I am shifting this pi bond towards this adjacent carbon which is adjacent to chlorine. or see dot. I'm shifting the pi bond towards that dot carbon. Right. Next, what will we get? You tell me what will we get? Here we will get positive charge or not. Do one thing. Take another step. Or you will get confusion. I'll explain in the two steps. Right. You can write directly, but next after listening one time, you can write direct reaction. Okay, you tell me. This chlorine containing carbon will get a positive charge. Positive charge. Why? Because it is losing the bond. It is losing the bond. And this carbon will get a negative charge. Negative charge. Because it is getting bond. Okay, right. Next, attach NH2 minus. Actually, we will explain this within a single step. But for first time, explaining step by step mechanism. Right. NH2 negative will attack this carbon. Okay? Right. Cl NH2. You can write NH2 this side also. Cl NH2, NH2 same, both are same. Okay? Actually, I am attaching NH2 this side now, but why I wrote that side? Any side I can write because this is sp3 hybridized. Are you getting what I am saying? This finger is here, this finger is NH2. I can write like this also. The reason is here, why I wrote like that. In the here negative. I forgot I wrote it. Is this step clear for everyone? Please tell me. Any doubt in this? Is this step okay for everyone? Sujan, Obed, is there any doubt in this step? First shift the pi bond towards one of the double bonded carbon. Then that carbon will get negative and carbon will get positive. Now attach the nucleophile because nucleophile requires positive center, positive charge. So we will get this intermediate. This is carbene ion. Carbene ion, aromatic aromatic nucleophilic substitution involves formation of carbene ion, aromatic nucleophilic substitution, aromatic electrophilic substitution. See, in aromatic electrophilic substitution, carbocation is formed, that is called sigma complex, Wheeland complex, we discussed already. Electrophilic sigma complex, Wheeland complex, loss of aromaticity. Clear? In the aromatic nucleophilic substitution, carbene ion is formed. Carbene ion is formed. And this is also lack of aromatic character. See, before attack of nucleophile, actually this is having aromatic character. 4n plus 2 pi electron rule is present here. After attack of NH2 nucleophile, it is losing its aromatic character. So step 1 is considered as loss of aromaticity. Intermediate do not contain aromatic character. Okay, deep question, very deep question. In the aromatic nucleophilic substitution reaction, lack of aromaticity is observed in the intermediate. Yes, this is intermediate. Aromatic character is not present. Why aromatic character is not present? This is sp3 carbon. If sp3 carbon is present, that is non-aromatic. If at least one sp3 carbon is present, that is non-aromatic. Clear? So that I wanted to say. In the first step, loss of aromaticity takes place. Okay, right. Remember this point. In both aromatic electrophilic substitution, aromatic nucleophilic substitution, aromatic character is losing in the first step. Got it? Right. You can write this in a single step by removing this, eliminating this. How can you write this? This is Cn, right? NO2. See, within single step, how can we write this? Shift this on this side. Or single step. So, within single step also you can write. Okay, simultaneously you can shift the pi bond and then you can attach nucleophile. Right. Now, observe this step. Aromaticity is lost. Aromaticity is lost. Here also aromaticity is not present. We know aromatic compounds are more stable. Aromatic compounds are more stable than non-aromatic. Non-aromatic are more stable than anti-aromatic. This is non-aromatic compound. Again, try to regain its aromatic character. Regain its aromatic character. Here, this is step 1. This total reaction is considered as a step 1. In step 2, what happens? Step 2 is very easy. This is not lengthy mechanism. This is one step only, a very small step. Another small step. Okay, not like aromatic electrophilic substitution reaction. That is lengthy. Now I am taking this. I am taking this intermediate. Okay. And one more point. I said that we know the reason why it is must and should the presence of strong minus M in ortho and in para. Why? Look at this. First we wrote one statement. Aryl halides when strong minus M groups are present in the ortho position or para position only undergo nucleophilic substitution reaction. Why? See the reason for that statement. What is the intermediate formed here? Carbene ion. Right? Carbene ions are stabilized by which groups? Carbene ions are stabilized by which groups? Plus M groups or minus M groups? Strong minus M groups only, na? According to general organic chemistry, GOC. Carbene ions are stabilized by which groups? Minus M groups. That's why minus M should be present. Clear. This carbene ion is stabilized by a resonance by minus M groups. That is the reason. If minus M is not present, then how this intermediate will be stabilized? Intermediate will not become stable, reaction will not take place. Clear? That is the reason. Presence of minus M is must and should in the ortho position or in the para position. Clear? Reason? Right. Next, see, this is loss of aromaticity. This is regain of aromaticity. Regain of aromaticity. Regain of aromaticity. Very simple. Get this all of this negative charge shifts in between these two carbons as a bond. This chlorine leaves. Okay. Got it. Double bond. How double bond is called? This negative charge is shifting as a bond. And H2. So Cl is leaving. Cl is leaving. This is aromatic nucleophilic substitution reaction mechanism. Any doubts in this? Please tell me. Is it okay for you? Any doubts in this? Everyone, boys, you also please respond. Sujan, Mohit, what about you? Girls, Adiba, Meenakshi, Bhakti, Harisha, Surabhi, everyone. Right. Okay. We completed mechanism of aromatic nucleophilic substitution. Now let us go to the model question. 99% you will give wrong answer only, right, for this question. Okay. I will explain reason later. First of all, you give the answer for my question. Which of the following readily participate in aromatic nucleophilic substitution reaction? Which of the following readily participate in? Tell me, aromatic nucleophilic substitution reaction. A and B. Give the answer. Which of the following readily participate in aromatic nucleophilic substitution? Both are satisfying the condition, right? Minus M group is present in the para. Minus M group is present in the para position, right? So both can, but which readily participate. Speed, rate is more for which? A or B? Think, try whether it is correct or wrong. Give the answer. Exactly. Yeah. See, in SN1 and then if electronegativity is more, then okay. Okay, almost closest answer, right? Right. Generally, in SN1 and SN2, if degree of alkylarity is same, then what we will say? We will say the leading ability, like this. Just a second. Which inhibitor? Nuclear. See, this is more reactive actually. B is more reactive. Okay. Because iodine is a good leader, better leader. If it is carbon and R2 is greater than R1, we know about this reactivity order, leaving abilities, everything. Okay. But we should not apply the concept, same concept in the aromatic nucleophilic substitution. Here, leaving ability is reverse here. In SN1 and SN2, iodine is a good leaving group. In aromatic nucleophilic substitution, iodine is a poor leaving group. Reverse, completely reverse. Very simple reason, see that. Why order is reversed? 99% what we will do after getting this question, aromatic nucleophilic substitution, first we will observe leaving ability. Iodine is a good leaving group. Select this. But that is wrong. Let us see why. As you imagine one nucleophile is present at this position. Okay, it is waiting to attack. Okay, it is ready to attack the positive charge. Nucleophile means the one which attacks positively charged carbon. Nucleophile is the one which attacks positively charged carbon, right? Any doubt in that? Right. See, extend this bond length. It's simple logic. Here carbon is there, here also carbon is there, right? This is negatively charged species. It always waits for positively charged center, right? Clear. Fluorine is connected to carbon. Fluorine is more withdrawing group, more electronegative group. Takes electron density. Most of the electron density will be towards fluorine side. So this carbon will get large positive side charge, large positive, huge positive, big positive. Iodine is a less electronegative. It takes only few electrons from this carbon, so it will get small positive. Okay? Large positive and small positive. Nucleophile is negative, so first it preferentially goes to large positively charged center. Clear? And fluorine leaves easily. That is the reason. Okay? Alpha carbon should have more positive charge. Alpha carbon means halogen attached carbon. Clear? That is the reason. This is not based on the leaving ability. This is based on the positive charge on the alpha carbon, halogen containing carbon. Clear, all of you? So, what we have to write in the aromatic nucleophilic substitution, the leaving ability is. Did you get this? All of you, any doubt in this? Girls, Surabhi, Bhakti, did you get this? So instead of this lengthy story, you can remember order, that is enough. Okay, in ARSN, in SNAR or ARSN, the order of leaving ability, of matrix is F minus greater than L minus greater than B R minus greater than I minus. Okay, so this is the leading cavity order in the aromatic nucleophilic substitution. Let us write one question on this. Okay, this is only the example, but with 4 options. Which of the following? Which of the following readily undergoes aromatic nucleophilic substitution reaction? Three options are there. What is the answer? Answer is tell me answer is A. Don't take unique like SN1 SN2 cases. Reverse case. Reverse. Right. Next, same question, but this was important model question. Which of the following readily undergoes SNAR? SNAR. Very easy to guess. What is the condition for aromatic nucleophilic substitution? Presence of strong minus entropy in ortho and barapination. Right? No answer. Option 2. Why option 2? This is also ortho only. This is also ortho. 2 are ortho. If more is the number of minus and groups, more will be the reaction rate. Okay, you can write. Rate is directly proportional to SNAR rate. SNAR rate is proportional to number of minus and groups. Important question. If more is the number of minus and groups, more will be the rate. Okay. 3 minus some groups are there. So carbanion stability is more. What is the intermediate in the mechanism? Carbanion is formed at the time I explained. Carbanions are stabilized by minus some groups. That is the reason. Right. Next, another distinct question, logical question. Right. Look at this question, all of you. Can you write the correct product for this? Identify the product. And let's do substitution at this position. Can you answer? Think carefully. Option D. D. Okay. D. You are saying second option or fourth option? But nothing is there, no? Only plain Benjamin. This is. Aromatic nucleophilic substitution, right? Substitution should take place. Option 1. See, option 1 is correct answer. Absolutely. What is the condition for aromatic nucleophilic substitution? Presence of strong minus-M in ortho and in para positions. In ortho and in para positions. Okay. To which halogen NO2 is in para position? That halogen only will. Very important example. Are you getting? First I given the condition. If minus M is present in para position or in ortho position, then only that halogen leaves. Aromatic nucleophilic takes place. Clear? Once you get this, to this chlorine, NO2 is in para position. NO2 is in para position. Look at this. NO2 is in para position. To this chlorine. So chlorine leaves. Chlorine leaves. To iodine, NO2 is in the meta position. Meta position do not works, right? Clear. So even though iodine is a better leaving group, iodine do not leaves because NO2 is not in para with respect to iodine. Clear? NO2 will affect on this chlorine only. Got it? Very important example. So Cl leaves. Which option that is? Cl is leaving. Option D. Otherwise you said option B or E? Said option. You said first option. But second one is the answer. I thought that you said first, second one. Okay, all of you got it? Parabolus to the chlorine. Clear? So chlorine is. First only given the condition na presence of minus M in ortho or in para. Clear? So 3 model questions in the ARS survey. 3 model questions. Clear? Once look at this one by one. Other than these 3, no question will come. If question will come on the mechanism, that will come. But I covered 3 model questions. Look at this. Which of the following readily undergoes question layer? Before that I just edited this. I given fluorine, chlorine, bromine. That is one model. Fluorine is more reactive. Okay. Next, this is second model question and third model question.